In this video, we're going to talk about composite functions. Before we can even talk about what a composite function is, we have to review function input basics. So what I mean by that is, what is a function? So a function has three moving parts. It has an input, an output, and the function itself. So when I input a number or a variable or something else into a function, the function translates it, does its algebraic magic, and then outputs some y value or f of x value. And in practice, this is what this looks like. So if I have some functions, so let's say I have this quadratic here, so f of x is equal to x squared minus x plus 2. So I can input different things. I can input numbers like 0 and -1, and I can also input expressions like x plus 2. So I can do some algebra here, right? So if I plug in 0, right, I put it in for every x that I have, and I simplify it, and I end up with the output of 2. And another way to think about that is an ordered pair with an x and a y that correspond on a graph, which we could totally graph as well. And then I can also plug in another number like -1, and I would get a number output much like when I plugged in 0. But the same process works for an expression like x plus 2 or x plus h. So I still plug in this input wherever I see an x in the original, so it gets squared and it gets subtracted, and then I work it all out, and I could write this as an ordered pair, although it's in terms of x, which is completely fine and very normal in mathematics, but this will come in handy in the rest of the video. Now we're ready to talk about what a composite function is. And that is technically a function within another function. So there's a lot of different notation you might see. You have this f of g, it kind of looks like fog. It really just means f composed with g. Or you can write it like this, f of g of x. This is a more common way to see it and to express it, but sometimes you do see that little open circle there. And in terms of input and output, if I had f of g of x, the first thing I look at is the thing on the inside. So I'm going to plug whatever the x is into g. Normally we're given whatever g of x is. So that's my input here. That becomes g of x. And then I take that thing and I put it in for wherever I see an x in f of x. So it becomes f of g of x. So that's my new output. It's like I have two inputs, one for just x that goes into g, and then all of g of x that goes into f. And while definitions are all well and good, let's actually put this into practice, so hopefully it makes a little bit more sense. So let's say I have two functions. I have f of x is equal to 2x squared minus 3, and I have g of x, which is equal to 4x. Let's do a couple examples with these two functions. So let's say I'm looking for f of g of x when x is 1. That's how we read that. So the first thing I'm going to do is input 1 into g of x. And when I do that, I put 1 in for x here, and so g of 1 is 4. Now I'm going to take that result and plug it in for f. So f of g of x when x is 1 is 29. Let's do another one, but let's switch the order. So let's still have our input be 1, but let's find g of f of x, which means that I'm going to first plug in 1 into f of x. So now that I have f of 1, I'm going to plug that output into my g of x. So I'm going to plug in -1 right there. And when I do that, my output for g of f of 1 is -4. And keeping with those same functions for f of x and g of x, I'm actually going to compose f within f of x, which means that I plug in -2 in for f of x, take that output and plug it back in to f of x. So let's see what that looks like. First thing I do is plug -2 into f of x, and I get 5. Then I take that output of 5 and plug it into f of x again, because that is the outside function, and that results with 47. Now let's compose a function within itself again, but let's use g. So let's find g of x when x is -1. So when I compose g of x into g of x when x is -1, the first time I plug in -1, I get -4, and then when I take -4 and plug that into g, I get -16. So let's do another kind of example. Let's say that I have two functions. I've got f of x is equal to this quadratic and g of x, which is equal to this linear function. Let's find f of g of x and the input will just be x. So that means that my output will be in terms of x because I'm not plugging in just a number. And let's find that function and its domain. And here's how I start this problem. I consider g of x as a function in green right here, and I am going to plug that 2x plus 3 in for wherever I see an x in my f of x, because f is the thing on the outside. So that means that g of x is my input. So I'm going to put a 2x plus 3 and square it, because that's the first term in f of x, and I'm going to add 3 times 2x plus 3, that quantity, because f of x is plus 3x, and then I just subtract 1. So from here, I just need to algebraically figure this all out. So I simplify f of g of x all down to this new quadratic, 4x squared plus 18x plus 17. And so I don't necessarily need to graph it to figure out the domain, but it's a nice visual to have. So that's going to be a positive quadratic, no restrictions to its domain, so its domain is all real numbers. So now let's try that same process, but using two different functions. So let's say my f of x is a rational function, so 4 all over x minus 1, and let's say the g of x is just 3x. So let's find f of g of x when our input is just x, so that means I'm going to have an x in my output function, and then let's find its domain. So what I do from here is I take my g of x and I input it into where there's an x in f, because that is my outside function. And really it becomes 4 all over 3x minus 1. And that's my function of f of g of x. So now I just need to figure out the domain, or in reality, what breaks the domain. And since my output, or my composite function, is a rational function, meaning that there's a variable in the denominator, that means that I'm going to have some kind of vertical asymptote, or at least a hole. So I'm not going to have a hole because I don't have the same factor on top and bottom, but I will have a vertical asymptote. So I set that equal to 0, and I solve for x is 1/3, which means that there's a vertical asymptote at 1/3. You could graph it as well and figure out the domain, but the domain is going to exist everywhere, so all real numbers except where x is 1/3. So you can write it an interval or a set builder. One last example here. So let's say f of x is x over 2, and I have g of x as the square root of the quantity of 4x plus 1. So now let's find g of f of x when the input is x. So that means, just like the last two problems, my output will likely have an x in it, so it's going to create a whole other function. So let's do that. Let's plug x into f, and then let's plug f of x into g of x. So from here, I take my f of x, which is x over 2, and I plug it in for that x, so that becomes x over 2 times 4, or 4x over 2. I can simplify that 4 over 2 to 2x plus 1. So this is my new function. It is a radical function, so in order to find the domain, I have to set that greater than or equal to 0, because I can have a radical that's 0 or greater, but not negative. So I simplify that down and I find that x has to be greater than or equal to -1/2. So if I also get an eye on this thing and I graph it, I see that it starts at -1/2 and goes on to an infinity there. So that means that I can express my domain in either interval or set builder. And that's going to do it for this video. Thanks for watching.